Suppose this is normal, this is R, this is mu1, this is mu2. This is refracted medium, this is incident medium. So here from diagram it is clear that I is greater than R. Taking both sides sine, so it is sine I greater than sine R. Now dividing both sides by sine R, so sine I divided by sine R greater than sine R upon sine R 1. Now from Snell's law, sine I upon sine R is mu2 upon mu1. Now from here, in place of sine I upon sine R, we can write mu2 upon mu1. So mu2 upon mu1 is greater than 1. So mu2 is greater than mu1. It means when light goes from medium 1 to medium 2 and it bends towards normal, it is bending towards normal, it means refractive index of this medium is greater than refractive index of the incident medium. So if refractive index of refracted medium is greater than refractive index of incident medium, then light bends towards normal. If a refractive index of refracted medium is greater than a refractive index of incident medium, then light bends towards normal when it goes from incident medium to refracted medium. So you can do it reverse. If I is less than this, if I is less than this will be less than 1, this will be less than this, and then it will go away from normal. So when light goes from one medium to other, it bends. Whether it will bend towards normal or away from normal will be decided by these two. Relation between real and apparent depth. This is denser medium, this is rarer medium. Refractive index of this medium is mu d, refractive index of this medium is mu r, and this is the interface, a surface separating the two media. Object in denser medium. And it is viewed from rarer medium. So our eye is here and it is object is here. Suppose this is the object O. So light which falls normally on the interface, it goes underweighted. But it is not only ray that come out of the surface, so many rays coming out. So this is another ray. Suppose get incident at this point. This is a real depth of object from the surface. Now this angle is said to be angle of incidence. As the ray is going from denser to rarer, so after when it goes from denser to rarer, ray bends away from normal, so it will go like this. If this ray go in our eye, so it appears that ray is coming from here, so image of this object will be visible here. Now suppose this point is P and this point is M. Here P is very close to M. This is called normal view. So all expression derived here is for normal view. Normal view means P is very close to M. Now this angle is angle of refraction. So this angle will be angle of refraction. This angle, these two parallel. So this angle and this angle, they will be equal angle. So this is also angle of refraction. Now here, if P is close to M, P is close to M, then these angles are a small angle. So this is our assumption, and this assumption you have to take throughout the derivation. P is very close to M, means point P is very close to point M, and that's called normal view. In these cases, angle I and R are small angles. You can assume this as a small angle, and you can apply then small angle approximation. Means I is equal to sin I is equal to tan I. So if angle is small, then I can write I, or I can write sin I can write tan I, and all are approximately equal. So this assumption we are going to take. Now here, this is incident medium, this is refracted medium. So if you apply Snell's law here, sin I upon sin R is equal to refractive index of refracted medium, that is in this case rarer medium, and refractive index is mu R, so it is mu R divided by a refractive index of incident medium. Here it is denser medium, so mu D. Now at place of sin I can write tan I because angle is small. At place of sin R I can write tan R, so tan I divided by tan R is equal to mu R over mu D. I can write it like this. Now here there are two triangles. Triangle, right angle triangle OMP, this right angle triangle OMP. If you write tan I, this angle is I, this angle will also be equal to I. This angle is R, and therefore this angle is R. So tan I will be equal to, in this right angle triangle, tan I perpendicular upon base. So PM upon MO. And MO means a real depth of this object from the surface. So it is PM upon real depth, I am writing R. Similarly, in right angle triangle IMP, if I write tan R, this will be perpendicular, that is PM divided by MI. So it is PM divided by, this is the depth our eye going to perceive. So this is called apparent depth, let it be A. I am writing apparent depth from A. So this will be apparent depth. So at place of MI I am writing A, apparent depth. real depth is r. Now tan I, tan r, put values of tan I and tan r in this equation. So here it is Pm divided by r whole divided by Pm divided by A is equal to mu r over mu d. Now Pm cancel, so it is A divided by r is equal to mu r over mu d. So this is the relation between apparent depth and real depth. Here A is apparent depth of object from the surface. It is apparent depth of object from surface. Surface means from here. Similarly, R is real depth of object from surface. Now, if our object is in rarer medium and it is viewed from denser medium, then we can derive formula like this. Object in rarer medium and viewed from denser medium. So here object is in rarer medium and viewed from denser medium. So ray going normal to the surface, it goes undeviated, and the ray incident here is not along normal, so it's going to deviate from its original path as it is entering into denser medium. So it will go like this, and this ray is received by observer. If you extend this ray, it appears that this ray is coming from here, so image will be seen here. So this observer will see image of object here. He not going to see this object, he will see image, and that is here. So this is real height of object from the surface, and this is apparent height. Apparent height. This angle is I, hence this angle is I, and this angle is R, hence this angle is R, therefore this angle is also R. Now if you take this point as M, this point as P, this is O and this is I. Here P again is very close to M, so normal view. What is tan I from this relation, from this triangle? Tan I is equal to perpendicular upon base, so PM upon MO. So it is PM upon R. And in this right angle triangle, if you write tan R and perpendicular upon base, PM divided by MI, so it is PM divided by apparent height A. Now again, if you apply Snell's law here, so it is sin I upon sin R is equal to refractive index of this medium, mu D, upon refractive index of this medium, mu R. As angles are small, so we can write it tan I, tan R is equal to mu D upon mu R. So tan I is PM divided by R, and tan R is PM divided by A is equal to mu D upon mu R. Now PM cancel, so A divided by R is mu D divided by mu R. So this is a relation between apparent height and real height of object from the surface. So from here height of object is this, and from here height of image is this. So this observer will see that object is at A height from the surface, while actually it is at R height from the surface. So he is going to observe greater height as compared to the real one.